Hi guys, I'm Emmanuel and this is group 13. So we are coming to present.
Hi guys, I'm Godwin representing Group 13, and today we are going to explain to you JK flip-flops. Okay, so here is our slide, and we have the introduction to flip-flops just to give you a little understanding of what flip-flops are. Flip-flops are basic building blocks of digital electronics. They are used to store one bit of data. So most of your memory cards and pen drives operate using hundreds of thousands of millions of flip-flops, right? And a single flip-flop can store one bit of data. So they have a stable state. That's they can be set to one state, which represents one bit of data. Either they are on or off. That's 1 or 0. So different types of flip-flops. We have SR flip-flops. That's for set reset flip-flop. D or data or relay flip-flop, T for toggle flip-flop, and then JK flip-flop. That's what we are doing today, JK flip-flops. So a JK flip-flop is a commonly used flip-flop. It's an improved version of the SR flip-flop, right? And I'll tell you why it's improved. The J stands for set and then the K stands for reset, right? So the reason why it's an improved version, okay, so I was saying that JK flip-flops are an improved version of SR flip-flops because they eliminate the undefined part of SR flip-flop part. For example, inside the SR flip-flop, right, when the first one is off and the second one is on, everything is reset. When the first one, that's the J, is on and the second one is off, is set. But then when both are on, the output is inverted, right? Yes. So this is the excitation table for JK flip-flop. So it's very simple. The JK flip-flop has a very interesting circuit diagram, and we are going to include that in the slides, in the next slide. It can be created using a NAND gate, NOR gate, and other components. So here is the image. You can see we have a NAND gate, an OR gate, NOR gate, all connected together, so that when one, you see that when one is on, the other is off. Basically, yes. So the working principle is basically it changes its state only at the edge of a clock signal. The inputs decide whether it is set, reset, toggled, or it retains its current state, and then it also gives feedback through the output. So applications of JK flip-flops, right? So first we have a binary counter. Now what a binary counter does is it counts the number of pulses coming from an input at a specific time. They process memory because they have no way of remembering past states. So it's just a digital counting device designed to count, right? Yeah. And then next we have a shift register. A shift register is something that allows input through a single data line and produces a parallel output. So input comes in and output goes out, and this is possible using a JK flip-flop to store and then transfer that binary data. Finally, we have frequency count. A frequency counter is an electronic instrument used for measuring frequency. It counts the number of cycles in an oscillation or pulses per second in a period of an electronic signal, right? I'm sure you've seen something like this in the hospital to count the frequency of a heartbeat or pulse. Yes, that's a frequency. So comparing JK with other flip-flops, we notice that, like I said, the JK is better than the SR because this one, there is no such thing as an invalid state, and it's also more versatile than the D flip-flop because it can be used for more stuff. It's also better than the T flip-flop because it ties the J and K flip-flop all together in one circuit. JK flip-flops are versatile, robust, and then they offer solutions to SR flip-flops problems. They can be used for so many stuff and memory devices. Thank you very much. We put together a little video to help you visualize JK flip-flops in action, and we hope you enjoy it.